All right. So today we're going to be having Professor Assad Oberai from USC give a talk called Bayesian Inference with Deep Generative Algorithms. Namely, he'll be talking about using GANs. Also, for everyone who's here, if you want to ask questions during the talk, please add them to the chat. We will also be having questions just after the talk, but there will be a fairly hard cutoff because soon after the talk, Dr. Oberai will be speaking to people one-on-one. He is the Vice Dean for Research and a Professor of Aerospace and Mechanical Engineering at Viterbi. He's a 2020 Fellow of the American Society of Mechanical Engineers, Fellow of American Institute of Medical and Biological Engineering, and the U.S. Association of Computational Mechanics. So in short, Professor Oberai is a very prestigious individual, and I'm glad that he came to USC in 2018. He's gotten several awards, including a Research Excellence Award from the School of Engineering at Rensselaer Polytechnic Institute, Outstanding Team Award from the same university, the Erasmus Mundus Master Course Lectureship from Universidad Politécnica de Catalunya in Barcelona. He's received a Humboldt Foundation Award for Experienced Researchers, the ASME Thomas J.R. Hughes Young Investigator Award. Of course, he's gotten an NSF Career Award, because who wouldn't with a guy of that prestige? Department of Engineering Early Career PI Award. He first got his bachelor's in engineering from Osmania University in India. He got a master's at UC Boulder in 1994 and a PhD at Stanford University in 1998, both in mechanical engineering. His past work includes being an assistant professor at Boston University from 2001 to 2005. And in 2006, he was in the Rensselaer Polytechnic Institute, where he was associate dean for research and graduate studies at the School of Engineering and associate director of the Scientific Computational Research Center. He joined USC again in 2018. And he works in the computational and leads the Computation and Data-Driven Discovery, or CD3 group. He creates and implements data and physics-based models and algorithms to solve problems in engineering and science, and problems that include detection, diagnosis, and care of cancer, understanding mechanics and physics and biology and medicine, modeling the evolution of multi-physics and multi-scale systems, and reduced order models for aerospace and mechanical systems. He's authored more than 100 articles on journals in these topics, and he's on the board of academic editors in 3 of these journals. So without further ado, let me have Assad start his talk.
Okay, thank you. So I assume everyone can hear me. What I'm going to do now is, of course, share my screen, and let's all hope that works well. So you can probably now see the PDF, and I'm going to go to full screen. So this is really the real test. If this works, then we are good to go. So let's see. Can everyone see the slides?
It is black right now, so we can't see it quite yet.
Okay. And you couldn't see it when I hit full screen, right? Before that, you could see it?
Yes.
Yeah, so that's not a good sign.
Uh-oh.
So you can see it now, right?
Yes, I can, yes.
So when I go to full screen, it doesn't work. Yeah, because I can see it now, but all you see is a black screen.
I'm afraid so. If we go back to the non-full screen version,
yes.
If you remove the I don't know what you call it, yes, I think that'll work pretty well.
Okay, this is pretty good, right? Good enough. Okay, I can do this. This is awesome. All right, let's do it this way. And really, there isn't that much fine print to read in this talk. So let's let's dive right in. Thanks everyone. Thanks for this invitation. It would have been great to be at ISI, but this is the next best thing. We get to talk to each other, and I'm really excited to talk to this group and get your feedback on the kind of stuff that we've been doing. So this is work that I've done with my PhD student Dhruv, and this is basically pretty much what his thesis is going to be about. It's doing Bayesian inference and then using GANs as priors in Bayesian inference. So that's the way to think about it. Here is an outline of what I'm going to do. Today, I will motivate the problem, spend quite some time motivating it. And there are two sort of different ways of motivating it. One is the field that I come from, which is sort of physics-based modeling. And the other is a field that you all are really familiar with, which is machine learning and data science. And there is motivation to be found in both those cases. So I'll do that. And then I'll quickly just recap the aspects of GANs that are important to our work, and then really come to the heart of the problem, which is how do we use GANs as priors, and then show you some hopefully convincing numerical results that these ideas are worth pursuing. All right, so that's the plan for today. I love when people ask me questions in the middle of the talk, but I realize it's not possible in a forum like this, so that's just too bad. But let's carry on. If I see,
let me interrupt you for a very brief moment. If you do see questions in the chat window, feel free to answer them. If you don't have time, that's fine. We can have those questions at the end.
All right, awesome. So I will look out for questions in the chat window if I can see it. All right. Okay. All right. So let's move on. Move on with the motivation. Okay. So one motivation for the work that I'm doing is solving what we call inverse problems in sort of physics-based computing. Right. So so this is a busy slide, but it really captures the essence of what we're trying to do. Okay. So usually in sort of physical sciences, there are physical principles that provide you, that give you well-posed mathematical models to map the state of a system to its response. So I'm denoting the state by this vector y, and the response by this vector x, and this is Rn, this is Rp, and usually there is a forward map that links the two. And so one way to think about this, think of y as representing the heat sources in a problem, the spatial distribution of heat sources, and think of x as a vector that represents the spatial distribution of temperature. So F is a map that will take the heat sources and map them to the temperature distribution, right? And so this map is well posed. It's you can do lots of really nice mathematics on it, right? It's unique. So so that's what a forward problem is. An inverse problem isn't that way. In an inverse problem, what you want to do is just the opposite. So from a response, you want to figure out what the state of the system is, right? So in this case, what you measure really is the response. I'm having some difficulties there, which is f of y here, plus a noisy version, right? So there is some noise there. And what you would like to do is recover the state of the system from that. And so given x hat, which is a noisy version of the response, you want to infer y. And this problem is not well posed, which means it doesn't have a unique solution. It's not stable, and there may not even be a solution that exists, right? So in order to tackle this, what people often do is they apply Bayesian inference, which is basically a statistical approach of formulating an inverse problems while accounting for uncertainty. So how does one do that? So let's move on. Okay, so what you do is you apply Bayes' rule or Bayes' theorem.
It looks like you're muted. Oh no, can anyone else hear this? I'm afraid you're muted, Dr. Assad.
No.
I cannot.
No.
I think it's his Wi-Fi because it shows us he's not muted.
Yeah. Oh no. We cannot hear you, Dr. Assad.
Maybe try to disable the video if it's a Wi-Fi issue.
Doctor, here, let me see if I can email him.
I think he might be able to hear us because he did disable the video just then.
Oh, yes.
Yeah, he can hear us. Yeah, there he says it in the chat.
Oh, shoot. But yeah, we can't hear you. Oh.
Maybe try to
rejoin, leave and rejoin.
Yeah, we did have a student who that happened to. We couldn't hear him, and then he just rejoined, and it worked. So that's possible, I guess.
Okay, let's try that.
He said he's doing it.
I'm going to pause the recording, and then I'll start when he rejoins.
Okay. All right. Okay. All right. So, what I was getting at was, in order to solve this inverse problem, people make use of Bayesian inference, and so the whole problem is posed as the following: you're given a measurement x, and you want to find out you're given a measurement which is a noisy measurement of the response, and you want to find out the state of the system. So you apply Bayes' rule, which says that that is equal to the probability of getting a response x for a given state y and the prior probability of y. So that's basically just the Bayes' rule. And this distribution here, which is the probability of x given y, can be written or can be also expressed in terms of the probability of the distribution corresponding to the noise here, which is p eta. So this can be written down as the difference between what you measure and the difference between that and what the forward model would predict for a given value of the state, right? So that's the likelihood function simplifies to this, and the prior sort of remains there. And so let's talk a little bit about the prior, because that's where really the magic is in this problem, right? So for the prior, what is the prior? So you think of the prior as anything that you know about the state, any information that you have about the state that you want to embed in this algorithm. So that's what the prior is. And how would you acquire this knowledge? You might have lots of old samples lying around of the state, right? So you might want to build a prior out of that. So that's one way. The other would be that you have some notion, right? So if you're trying to, if you talk about heat sources, you might say, well, the lowest intensity is 0, and the maximum intensity, I don't know, is like 10,000 in some units, right? So you might have some bounds on its spatial variation. So you can take all of these to generate this density or the prior density, and then use it here. And then once you use it here, then you can compute the posterior, which is basically an update, saying, now that I have a measurement, what is the distribution of this field that I'm trying to recover look like? All right, so that's Bayesian inference. And let's move on. So if this is a formula, how does one actually use this formula? What are the steps that you have to go through in order to use this formula? So the first step is you take your prior information and you construct a density out of it. Now this sounds simpler. It sounds simpler than what it really is, because we'll get to it, because it's not that easy to construct this prior. And then the second step is, this is the formula which tells you that the posterior is proportional to the product of these two, right? So for a given value of y, which is a guess at the state of the system, I can compute f of y, which is my forward model, no problem. I know what x hat is, I can put it in here. I know what p eta is. So I can actually compute the value of this distribution up to a multiplicative constant at that value, right? And so then I can do that. I can do that many times. And then I can maybe train an MC algorithm to learn this distribution, right? So that's the second step. So the first step is construct the prior. The second step is use this formula to be able to sample from the posterior. Now, both of these steps have problems, and these are the challenges, all right? So the challenges, the first challenge really is generating prior distributions for complex cases. So let me give you an example of what that challenge might look like. A typical prior that gets used a lot is a Gaussian prior, right? And this is basically a Gaussian prior for a vector. And what this is basically saying is that the value close to 0 is very likely, values that are large are far away from zero are very unlikely, and there is a Gaussian distribution that tells you how this decays. Now that's fine if that's what your prior is. But if your prior looks something like this, so what I've taken here is a snapshot, let's say, of the field that we're trying to infer, right? So this is basically, let's say, the intensity of the heat sources. And if it looks something like this, and these are 4 snapshots, and maybe I had 20,000 of these, right? I really cannot come up with a distribution which will actually give me this, right? It's really hard. It's a hard mathematical problem to solve, right? So this is just one instance, but I can have lots of other instances where it's simply very hard to come up with a mathematical description of the prior. So you know, that's one stumbling block in Bayesian inference applied to solving physical or physics-based inverse problems. What is the other challenge? The other challenge is that when you're trying to recover fields like this, they are defined spatially, and they're defined on a grid. And that grid is usually 100 by 100, 1,000 by 1,000, or 100 by 100 by 100. So what you're trying to do is infer a distribution of variables where the number of variables is very large, right? And then sampling becomes really hard to try and train an MCMC algorithm actually to basically learn this distribution is nearly impossible. So that's another problem. So this, and of course, there are approaches that are out there that address this sort of, you know, let's say advanced MCMC algorithms or variational Bayes or reduction in order Y or F. You can do all of that stuff, but that is an issue, right? So these are 2 challenges to Bayesian inference. And what I'm trying to say here is that to address both of these challenges, we can use GANs, that there is a possibility of using GANs to address these challenges and do something useful with Bayesian inference applied to physics-based problems. So that's really the first motivation for this work. The second motivation actually stems in machine learning or deep learning, right? So I think all of you who are listening to this talk probably know this, that if you train a classifier on a given data set and then use that classifier on a different data set, very often you will get predictions, you know, soft max values, right? Which will be very large. So clearly this shouldn't be, because this is, you know, this classifier was not trained on this. It's not supposed to know anything about this data set, but yet the prediction is overconfident, right? And this can have repercussions in the downstream task, right? So if you have very confident predictions, you're going to base a decision off of that, and that decision will be completely wrong, and things can go wrong and have gone wrong. I think everyone knows that. And so how do you get over this? The way to get over this is not only make a prediction, but also quantify the uncertainty in that prediction, right? And you can use that to then inform your downstream task. You can also use that to actually design an experiment. So if the uncertainty is high in a given region, why not go and find more information about that region? And that's called active learning, right? So uncertainty quantification plays a really important role in machine learning. And there is a growing and a large body of literature that's sort of dedicated to discussing this, right? MCMC dropouts is one, stochastic variational inference, deep ensembles, and other hybrid methods. So in any case, so there is a lot of stuff going on, but I guess my point here is the techniques that we'll be talking about here, in particular, the idea of using GANs as priors in Bayesian inference can also tackle this problem. They can also be used to tackle the problem of quantifying uncertainty in machine or deep learning. So I'm going to give you examples of both, right? So that's the plan. Okay, so with that, let's sort of dig in a little bit now and develop the machinery that's necessary to do the kind of stuff we want to do. Okay, so a quick overview of GAN, only covering the stuff that's relevant to today's talk, right? So, you know, introduced by Goodfellow in 2014, and as you know, been used widely for many different things. But in our context, what's important here is the following, right? A GAN takes a latent vector, which is Rm, where m is relatively small, like 100 maybe, or maybe, yeah, a few hundred. And then through a deep neural network, and this could comprise of sort of upscaling type convolution layers and then fully connected layers, it maps it into a field, which is Rn, but n is much bigger than m here, right? And so the latent vector is chosen from a very simple distribution, Gaussian or uniform, right? And then as it maps it through this, it creates samples that can belong to a very complex distribution because this map is really, really complex. And it's parameterized by this weights theta, right? And so you generate lots of these. And then in addition to this, you have lots of real samples. And you take the real and the fake samples that you generate and you push them through a discriminator. And this discriminator has its own weights. And the job of the discriminator is to discriminate. So if you give it a sample that comes from the generator, it should give you a 0. If you give it a sample that comes, which is real, it gives you a value of 1, right? And the way these components are trained is in an adversarial manner, right? So what does that mean? Well, what that means is that they're trained through this objective function. So if you look at each of these terms here, so when you choose Y, which is the field that you're trying to create the GAN for, from the distribution of samples that is available, right? So this is the expectation of D, the discriminator operating on Y, right? So for the discriminator, what you would like is for this to be 1. So you would like this expectation to be maximized, right? And then if you look at this term, this is all the Z's that are sampled that are coming through the generator. These are the fake samples. So as far as the discriminator is concerned, it would like this to be 0. And so 1 minus 0. So what it would like to do is also maximize this term, right? So the weights of the discriminator, that is mu, are determined by maximizing this argument. So you have argmax of L, whereas the weights of the generator, which is trying to fool the discriminator, are determined by minimizing this argument, right? It would really like D of G of Z to be equal to 1, which is basically the minima of this. So you get a min-max problem. So the weights are determined through a min-max problem, and that is what people call an adversarial training, right? Or whatever, yeah, that is adversarial training. Regardless, what you can show, and this is really key in our derivation, this is going to be the most important thing about a GAN that we'll use, that if you have enough capacity, which basically means you have a rich enough network, and if you have sufficient training, which basically means if you have enough samples, you can prove the following. You can prove that any point estimate that you want to compute over the true distribution, right? That's what this thing is equal to the point estimated computed by sampling from Z, passing that through G, which is the generator, and then passing it through the function that computes the point estimate, right? So this is the critical part. This is basically saying that your GAN has learned, in some sense, the underlying distribution. But this is in a weak sense. And as far as I'm concerned, this is all you can prove for a GAN. You cannot prove strong convergence of these distributions. I cannot say PY equals PZ or PZ mapped forward. That would be incorrect. I can only say this in a weak sense, okay? But that's all we need, all right? So this is basically the most important part of a GAN that we'll be using. All right, so far so good. So let's move on. Okay, and people know that GANs can do amazing things. I bet you've seen this, and this is already quite old, right? This is 2017, where someone took the Celeb A data set, right? So all the images that are down here, right, down here, are the training images, right? And they trained a GAN. And so, the number of pixels and RGB here was such that each image could basically belong to Rn, where n was about 3 million. And the GAN that was trained had a latent space of only 512, right? So that's some serious sort of reduced order modeling going on. And once that GAN was trained, by sampling randomly from that GAN, you were able to generate the images that appear in the top row here, right? So these are fake celebrities, but they look like real celebrities. They certainly don't look like me. So so in any case, so this is this is sort of again like 2 years old. So maybe by now there are even more amazing pictures that you can generate out of a GAN. But the point I'm trying to make here is GAN, the way I look at it, is basically a tool which can represent really complex distributions using a very small latent space. And that's the part of it that we're going to make use of. Okay, so that's that. Now let's talk about using GANs as priors in both physics-based problems and data-driven problems. So remember, we had 2 motivations to begin with. Let's address both of those. Okay, so coming back to the physics-based inference problem, right? So let me remind you what that problem was. So we want to infer the state, which is given by this vector y, and we have a sample set which contains many realizations of y, and we're going to build a prior out of this. In addition, we have a knowledge through mathematics and physics of this forward map, which maps the state to the response. So we have that. And in addition, we have one measurement, a noisy measurement, x hat. And what we would like to do, and of course, we had some characterization of the noise in the system, in the measurement. And what we would like to do is infer the state that corresponds to this measurement, right? And it's not going to be one state, it's going to be a distribution of states. And that's what we'd like to infer, okay? So that's the inverse problem we want to solve. So the first step in our approach is actually to take this sample set, you would have guessed this, right? And train a GAN with a generator G of Z. So we've now basically trained a GAN to be a prior in a Bayesian inference problem. So let me talk to you how that actually works, right? So once you're done training this GAN, I just talked about the property of a GAN, right? So once it's done training, I can calculate any point estimate over the prior, right, M of Y, by simply sampling over the latent space of the GAN, which is an easy sampling task, passing it through the generator, and then then sort of operating on that with this function that defines the point estimate that I want to calculate, and then computing the expectation on that, right? That's the property of the GAN. So we talked about this. This is fine, but this is over the prior. I don't want to do this over the prior. I want to be able to do this over the posterior, right? So this is, we are not fully there, right? So how do I transform something like this so that this Y is not over the prior, but is over the posterior? Well, let's look at the definition of the posterior. And this is where Bayes' rule or Bayesian inference comes in. So the posterior given an X is P eta of X hat minus F of Y. So remember, P is actually proportional to this, right? Z is a constant that I don't know. So P eta here is the distribution for the noise, X hat is the measurement, and F of Y is the forward operator, and PY is the prior, right? So that's how the posterior is related to the prior. So what I can do is, if I go back to this formula, and for a specific case of this M, I'm going to choose M is some other function L times precisely this term, basically the part in the posterior that is not the prior, right? And then I substitute that in here. What you will see is through that simple trick, out here I'm going to get, M is L times P eta divided by Z, right? And Y is sampled from the prior. And then basically this left-hand side is nothing but I am computing L of Y with the Y, or the expectation of L of Y, where the Y is sampled from the posterior. So the left-hand side becomes what I want it to become. And the right-hand side, well, what is the right-hand side? The right-hand side becomes, again, it's L of G of Z, right? So it's the same point estimate on both sides, right? But now Z is sampled from not PZ, not the prior in the latent space, but the prior in the, but the posterior in the latent space. And that is related to the prior in the latent space through the likelihood term. And it's as simple as that, right? So what we've done is basically used a GAN as a prior and then come up with a formula to compute the posterior, or to compute any point estimate for the posterior by sampling in the latent space. And that's what this formula is. And that's it. This is it. I mean, this is the crux of everything that we're going to be doing, okay? So really, it becomes, this really becomes the key thing that we are looking at, the posterior in the latent space, right? And so, and that's what I'm saying here. So sampling of Y from the posterior for Y is the same as sampling from Z from the posterior in the latent space. It's basically the push forward of that with respect to this transformation. That's what it is. But what's the advantage of this? The advantage of this is, since we're using GANs, GANs can represent really complex priors. So that limitation that we had earlier, where I had to write down a mathematical equation for my prior, goes away, right? I can say the prior is basically a celebrity face, and I can solve a physics-based inverse problem on that, right? So you can imagine, like, maybe I have a infrared camera and I'm able to, check the temperature on a person's face. Then by mapping it onto this prior, I can probably get a pretty good representation of what their real face looks like, which is scary, but one can do that. So that's one advantage. The other advantage is that the size of the latent space is much smaller than the size of, this really had to be Y here, the state space. And then you can do, when you're trying to sort of construct, let's say, a Markov chain Monte Carlo algorithm to basically, to sample the posterior, it makes it much easier because you have a much smaller dimensional space to sort of train this algorithm on, right? So step 2 would be, once we know what PZ post is, right? Once we can evaluate this value of PZ post for a given Z up to a multiplicative constant, you can train a Markov chain in order to, whose stationary point will give you, or will be close to this posterior. And once you have that, then you can calculate any point estimate that you want by simply sampling from that Markov chain. So 3 steps. Step 1, train a GAN, right? Using all the realizations of the state that you have. Step 2, train a Markov chain algorithm using the definition of PZ post. And step 3, use that Markov chain to sample as much as you want. And then you're able to quantify uncertainty the way you want it, okay? Of course, you might say that, training a Markov chain is too much. I really don't want it. All I really want to do is find the most likely solution, right? Then what you can do is you can go back to the definition of this posterior for Z that's available, and you can look for the Z that maximizes this. And the solution of that is basically solving an optimization problem, which is, of course, much less expensive than trying to train a Markov chain to get to the whose steady state should be equal to PZ post, right? So that's a way out. It's a shortcut. If all you're really interested in is the map, or the most likely, or the maximum a posteriori estimate. Okay, so that's how you would solve physics-based inference problem using this strategy. How would you solve data-driven problems? So let's consider a standard supervised learning problem, right? So you're given an image, and you have a label, and you want to now find the label, but with quantified certainty, right? So how would you do that? So here's how you would do that. So now what you do is so the image now is given by X, and the label is given by Y. So you take the image and the label pairs, right, and combine them into this vector U. And so your training set is a lot of values of U, right? And then what is your measurement, right? So when you put, that's going to be a training set, and then you'll be given something. Well, you'll be given an image, right? So what you'll be given is IX, which is an indicator function operating on U, which will just extract the image part of it, right? And so not only that, you will be given that, but maybe a noisy version of that. So your measurement for X hat will be this operator on U plus some noise. And of course, you will have some estimate of what this noise looks like. And the problem that you want to solve, so I'm going to cast this problem exactly in the same framework as the physics-based inference problem. So the problem I want to solve is, I want to determine the distribution of Y. Actually, I want to determine the distribution of U, both X and Y. Remember what Y is. Y is the label, and X is the image, right? So I want to determine the distribution of Y, which contains the label, given a noisy image, right? So that's the inverse problem, or the inference problem that I want to solve. Once I pose it this way, I can use exactly what I did in the previous part of this talk, and everything just completely goes through. I don't have to change anything except just rewrite the formulas, right? So the step 1 is still the same. Step 1 is take the image and the label pairs, right? And train a GAN, and let the generator of the GAN be called G of Z, okay? Okay, so then this is what I'm trying to say here. Then using Bayes' rule and using what I know about a GAN, I can prove that any, then of course, for any point estimate that I want to calculate for the posterior, given the measurement X hat, right? I can calculate it by sampling from the latent space, as long as I sample from PZ post, where PZ post is related to the prior latent space PZ, right? So the simple one, which is, this is like Gaussian or normal, through times this P eta, right? Where P eta is given by, is basically the distribution for the noise, right? So okay, so this basically says that sampling from the posterior of view is the same as sampling from the posterior of the latent space, recognizing that you have to make this transformation to go from the latent space to the state space. And here the state space is the image and the label, right? And so in order to do that, since I have an explicit expression of this up to a multiplicative constant, I'm going to train a Markov chain, again, whose sort of stationary point will converge to PZ post. So that'll be step 2. And then I'll sample from that. And then I can compute, really this should be L of U. So this is a typo. Then I can compute any point estimate that I want, right? Which means basically what it really means is now if you give me an image, I will be able to compute, not only an answer, but a whole distribution of answers of what the labels might be. So I would be able to quantify uncertainty fully in that image. Okay, so that's how you would use this for solving data-driven inference problems. In this case, supervised learning problems. All right, so that's pretty much it. So that's the machinery of what we are doing. Now let's look at some examples, some numerical examples, sort of drawn both from the world of physics and then also from the world of data, and see what we get out of it, right? Okay, here we go. So the first problem is physics-driven problem. So this is where, this is the first part of the talk where there is going to be a forward operator, and we'll make a measurement and we'll try and infer the state. So what is this physics-based problem we're solving? So what we want to infer is exactly what I've been talking about. Heat sources, right? On a square domain, there are some heat sources, and I want to infer that. And the way I will represent those is by taking, dividing that domain into a 64 by 64 grid and saying what's the value on each grid point, okay? What's the forward map? So the forward map is basically heat, the heat equation, right? Basically something that maps that heat source to a temperature. So, Laplacian of temperature equals the source. And so that's the forward map. And so my measurement is going to be a noisy version of the temperature. And then what I would like to do is take that noisy version of temperature and recover the heat sources that generated that. And I'm going to add a lot of noise to my measurement, right? And then I am going to define a prior, but my prior is going to be based on samples, right? And for that, I'm going to use GAN. And that's basically what I'm trying to demonstrate here. Okay, so what is my prior? So
wait, if I may ask you a question. It would seem that your method is sensitive to the estimate of the noise distribution. I mean, you have to assume, for example, that it's a Gaussian with this particular distribution. How do we determine noise distribution a priori, though?
Yeah, that's a good question. So while you have to assume something, in general, it's pretty robust to the assumption that you make. So if you have some idea, like, if it's Poisson noise or more or less Poisson or more or less Gaussian, you need to know something. But it could be a pretty wide variety of models that you can put in there. There are techniques where finding out what the noise is becomes a part of the learning process too. So you can sort of do hierarchical Bayesian techniques to do that. But in general, it's pretty robust. Yeah.
Great, thank you.
Okay. All right. So let's do this now. So let me show you what the prior looks like, right? So this is all fake, right? So I'm going to construct this. So I'm going to say what I really have are 4 hotspots, and they can be anywhere, but they're of a given radius and they can overlap, right? So I generate lots of random images that look like this, right? So again, like if I go back a little, they can be together, there can be some overlap, maybe no overlap. And then I train a GAN to do this. Basically, I generate lots of these, train a GAN, and then I ask the GAN to, just to make sure it's doing the right thing. And this is a sample produced by the GAN, which is pretty cool. It's figured out that where things overlap, it needs to add things up. And where they don't overlap, doesn't need to add things up. And where 3 things overlap, it needs to add more stuff. And usually there are just 4 circles. So the GAN has basically learned what I wanted it to learn. Right, here is another sample generated by the GAN. Okay, so once this is done, this is the step 1 of my algorithm. I'm happy with this. Right, here's another estimate. step two, right? So step two would be, well, let's get to step two in a second. So now let's test the algorithm. So step two would be, I have the prior trained, right? And then what I need to do is for every value that I sample from the latent space, I can generate the posterior up to a multiplicative constant. I train an MCMC algorithm based on that. And once that's done, I can compute, I can sample from it and compute any point estimate, right? So now let me test that. Let me test that approach. So I give a problem for which I know the solution. So the 4 hotspots are completely distinct in this case. They're sitting in the corners. And this is what the distribution of the hotspots looks like, right? This is the distribution of the temperature, right? So you solve the heat conduction problem. Of course, it blurs everything out, right? Think of the heat conduction problem as a blurring kernel. It's exactly that, right? So it's going to blur everything. And so given this, I want to now recover, not this actually, given this, right? So I add some noise, a lot of noise. So now given this, I want to now recover what I started out with, which is the 4 hotspots. And this is the most likely estimate I get from the MCMC sampler. So on the left is the true solution. You could see like the intensity was 0.25. The scales here don't match up, but you will notice that the intensity in each of these is very close to 0.25. And the location is really good. It's basically got the 4 hotspots just right. And it's basically, what's happened here is the following. The forward problem is such that you lose information, right? It's a blurring kernel, so you're gonna lose information. Where is that information coming from? It's coming from the prior, because the prior is telling you of all the possible things that could have given you that blurred temperature. The ones that we're really looking for are these sort of distribution which contains 4 hotspots. And so then once you say that, then the range of your possible solution becomes much smaller, right? And so this is the most likely solution that you get. But you can compute more statistics. So you can compute the mean. So this is the mean of the distribution that looks like. And you can see it's very confident that the center, that in the center of these regions, there is a hotspot, but it's not so sure about the boundaries, right? Because I could move these hotspots around a little bit and the temperature would not change that much, right? And I can actually even compute the variance. So this is the standard deviation. And this is telling me where I'm most uncertain. I'm most uncertain around these rings, which correspond to the boundaries of the hotspots, which is what you would expect. I'm pretty certain there is no hotspot here. I'm pretty certain there is a hotspot here, but around these rings, I don't know, right? So that's useful information in terms of quantifying uncertainty. Okay, let's move right on. And now maybe solve a problem which is from the world of machine learning, right? So sort of deep learning, let's say. Okay, so this is a simple classification problem, nothing fancy, right? So in this case, what we're going to do is our input is going to be the MNIST data set. So the images are X, the label is Y, right? Here is a snapshot of the MNIST data set. And what we're going to do is take some part of the MNIST data set and take the images and the labels, concatenate them and train a GAN. So the GAN now learns the underlying distribution of the images and the labels, right? And then using the approach that I talked about earlier, right? The same approach, Bayesian inference, I'm going to take a noisy image and then from that predict, the labels, not only the labels, but statistics on the labels and statistics on the images too. And when I do that, what I can tell you is that if I look at the most likely estimate, right, and say that that is my answer, I get about 97% accuracy. I can do better too, but this is comparable with, probably the best accuracy that you can get given that network. And that's fine, but that's not really the point of this, right? The point of this is what can you do about estimating uncertainty, right? So one standard test that people do is they train it on a given data set and then they bring in another data set which has nothing to do with the data set that was trained on. And then they say, can your algorithm tell me that this is now a different data set, right? This is called out of distribution detection. So for that, we use not MNIST, right? And then what we do is, as a measure of determining whether this thing is out of distribution or not, we measure the distance between, now here, this is critical, the noisy image that you gave me, the input, and the most likely image that I recover. Remember, when I recover not only, the label, I also recover the most likely image within that distribution, right? So corresponding to that image that you gave me, right? Now, if the distance between these two is large, that means what you gave me was basically not in that prior distribution, which means it is out of distribution. If this distance is small, then this tells me that what you've given me is within the distribution and I have confidence in my prediction. And this is a really good measure of basically separating the two distributions. So if I take x minus x map, take the norm of that and look at each case taken from MNIST and not MNIST, I get a perfect separation, right? So for MNIST, this distance is small for all the MNIST that I've tested it with. And for all not MNIST, this distance is large. You get like 100% accuracy in sort of in distinguishing these two. Okay, so that's this test, right? I noticed there's a question here. Why do you need labels for OOD detection? That's a good question. We don't, sorry. So in this case, I'm not using labels. I'm computing the label, but I'm not using it, right? So the algorithm will work something like this. It would be like, check this value. If this value is large, then tell the user, you've never seen this before, so don't trust whatever I say. And that's the end of it. If this value is small, then predict the label and give it to the user. Hopefully that answers your question, Alan.
Can I ask you a question?
Yes.
I saw that you report your performance, but have you compared your method against more traditional methods, like for the source recovery problem? I think I've seen people use compressive sensing before that they estimate the location. Have you compared against something more traditional?
Yeah, good question. So we've compared stuff with using like, H1 and L2 priors. Compressed sensing would basically end up being like total variation, will lead to a total variation type prior.
Yeah, yes.
And we haven't explicitly compared it against that. Total variation, I think, will do reasonably well. But if you think about it, I could fool total variation also, right? So I guess, yeah.
But
so,
in natural images, usually it's a good prior. But I think you're right that you may find some problem in which that prior is not a good prior.
Exactly. Yeah. So I think, so we can come back to that. All right. So let me sort of go on to the next problem, which is image in painting. And image in painting can also be posed exactly in this framework, right? So that's the cool part here. You can take all these problems and they're sort of all in the same framework. And why is it in the same framework? Because I think you would have probably already guessed it, right? So the part of the image that you supply to me, right? That is the part that is known, that's the X hat. And the part that is not known is Y hat, is what I'm going to predict. But actually I predict not only X hat, not only the part that's not there, I'm actually going to predict everything, right? Because that's what I'm going to train a GAN on. So once again, I take MNIST, train a GAN on the whole images. So by the way, now U here is an image. So this part is image in painting. It has nothing to do with labels, right? So U is the entire image. So I train my GAN on all the images in MNIST, right? And then what I'm going to say, my measurement is going to be a noisy, occluded version of an image. I'm going to call that X hat. And then I would ask you to predict the posterior corresponding to that. So here is one measurement. You can clearly see it's for 5 and there's noise here. And you can also see that I've occluded a part of it. And then I train I go through this whole procedure that I talked about, train the MCMC, and then compute, the map. I compute the mean, and I also compute the variance, right? And in this case, what you see is the map and the mean are very close to each other, and they're right. They got the digit 5 right, and the variance is small. So then I say, let's push this a little bit. So I increase the size of the window. Once again, it gets 5, right? But you notice that the variance is starting to increase, right? And then I say, let's really push this. So I almost block everything. And now it's lost, right? So it makes this beautiful 8 as the most likely solution. And if this is all you got, you'd be in trouble, right? Because if your downstream task was, I don't know, hit the nuclear button if you see 8, then you've just made a big mistake, right? But of course, if you do UQ, if you do uncertainty quantification, you will look at the mean and say, oh my gosh, that's really smeared out. I should not trust it. And if you look at the variance, you'll say the variance is huge, so I should really not trust it. So you will not hit the nuke button, right? And you'll save the world. There was a question somewhere. Let's see. Oh, 5 minutes to go. Okay, sorry. I am going to speed up, right? And then the same applies for this digit 3, okay? I'm actually almost second last slide almost, so I'm not too far. Okay, here is another interesting thing you can do with image in painting. So in this case, we took celeb A, trained GAN on celeb A, and the whole image is basically you. And then we are trying to do image in painting, right? But in a more interesting way. So the top part, the top row here is the true image, right? This here is the measurement. So initially the measurement is nothing, right? We're seeing nothing, right? And so we ask this algorithm to produce the map. The map looks like this. The mean is a blurry image of a human being, which makes sense. And the variance is large everywhere, right? Then we say, okay, let's be clever about it. So let's find the region where the variance is higher, and let's reveal the noisy version of the true image only in that region. So now we know this. Now make another prediction. So the map is this, the mean is this, and the variance is this, right? So the variance where we opened up that little tile is small now. Okay, that's interesting. So, but now the variance here is the largest. So we open up this tile, and now we get a map and a mean and a variance. And then we open up this tile. And so this is our measurement, a map and a mean and a variance. And we keep going, and we get to this point, which is about 8 tiles that have been opened up. And now the variance is small everywhere. So you should be happy. And the map and the mean start to look a lot like each other, which is incidentally pretty close to the true image, right? So this is giving me confidence that I know enough about this that I can stop at this point, right? So this is what you would say, I guess, active learning, because you designed what you wanted to reveal based on your solution. Okay, that's where I wanted to end. So I think I'm right on time. So, you know, what have we done here? I think the way to think about this is we've used GANs or found a way of using GANs as priors, both in physics-driven and data-driven Bayesian inference. There are many related works, I think, and it would take a long time to list those. But you know, conditional GANs is obviously somehow related to this. There are other techniques out there which are related to this. What I like about this is it gives me a kind of a unified formulation for doing lots of things: classification, denoising, in painting, bring in physics, and all that stuff. And the way it really works, the reason it works is we rely on the ability of a GAN to represent complex prior distributions using a small dimensional space. And then, you know, the advantage, I think, is like if there is a take-home message from all of this is when you do ML, when you do deep learning or whatever, it's always good to think about, are you saying something about the confidence in your estimate? Because I feel like for a long time, it was probably neglected. It's certainly received much more attention now that it's worth thinking about, right? Because, you know, the repercussions of not doing that can be pretty significant. And then where are we going further? You know, normalizing flows are really interesting generative algorithms. And there is a question of how you might use normalizing flows in this context. And so that's what we're thinking about right now. Okay, thank you.
All right, thank you so much, Assad. Now you will be talking to Greg Versteeg. But in the meantime, you know, let's have everyone give him a sort of virtual round of applause. This was very good. It was great hearing this.
Thank you. Thanks, everyone. Oh, and by all means, feel free to reach out to me or my student Dhruv. We'll be happy to chat about it. All this work really is in this X-archive document here. You can go read it and tell us where we made big mistakes. All right.
Great.
Thanks, Assad.
Yeah, thank you so much. I'll stop recording now.
Greetings.
Okay, I will be ending this meeting